Well, we've looked at two examples of how to use the Rice expression now. Both of them works of fiction on a certain level. In one case, we started knowing all of the equilibrium concentrations, and we calculated K. In the other one, we decided to do a little bit of a brain teaser, where I'd give you certain of the known quantities in the Rice expression and ask you to fill in everything else. What I want to do now, as I get to the third example, is show you the way the world really works, the way people really use the Rice expression, because it fits exactly with how experiments work. Here's how experiments really work. I walk in one day, and I decide to run a reaction, and I know what my reaction is, and so I go over and I get off of the shelf some of the materials that I'm interested in working with. Suppose I'm wanting to do the Haber process. And I decide that I'm going to get some hydrogen and some nitrogen off the shelf, maybe a little bit of ammonia, and I'm going to throw them into a container, into a system, and I'm going to say, ready, set, go. And so they go. And I wait for a while. I may wait for 1/10 of a second. I may wait for 6 hours. But when it's all done, I am at equilibrium. Now that I'm at equilibrium, I can ask myself the question, what are those equilibrium values equal to? What are those values? You see, that's a problem there, because you realize that I don't have all that much information going for me. So for example, suppose I started by saying, you know, I don't really have any hydrogen or nitrogen around, but I've got 0.1 molar ammonia. I'm just going to put some ammonia into a vat, seal it off, go away for a while and come back. I want to know what the equilibrium concentrations of all of these values are. Well, we already know that that's not something you're going to be able to find without more information. And the traditional piece of information that's missing is something that we know we can always have around, we can always have available. That traditional piece of information is an equilibrium constant. Because remember, constants are in fact constants. Ammonia, in its reaction in the Haber process here, really does have an equilibrium constant at a certain temperature. So I can always go find that. So I throw some ammonia into a container, and then I walk over to the shelf, and I pull off of the shelf my thermodynamic tables. And I open them up, and I turn to the page, and there it is, the Haber process right there. K equals 3.8. So I know now not just my starting materials, which I have control of, but I know K because I got it out of a book. That's the practical experiment we always do. The one where you know the equilibrium constant, and you know the starting materials, and you want to know what happens at equilibrium. This is the problem that you're going to work for the rest of the course.